Hi everyone, in this video we're going to talk about section 3.2b, which is about extreme values of functions. So in our last video we talked about the extreme value theorem, and really the math that we were doing was more pre-calculus. We looked at graphs and we were able to identify where maxes and mins were. And when we were on a closed interval, we could identify an absolute maximum and an absolute minimum. In this video, we're going to use calculus to analytically determine where absolute and local extrema come from in functions. Now, this video is made from splicing a couple of other old videos together, so bear with me if it seems a little bit rough. Enjoy!
First of all, to find extreme values of the function over a closed interval, we have to take those endpoints into account. So we're not only talking about in the middle where we have extreme values. Endpoints can also be extreme values. So if we're trying to find where those are, we have to take the endpoints into consideration. Next thing, if an extreme value doesn't occur at that endpoint, it has to occur at a value c where either the derivative is equal to 0 or where the derivative doesn't exist, so where the derivative is undefined. Now, you'll notice that there's a bold statement. This is really important. We don't just bold things for no reason. So while these conditions have to be met for an extreme value, their existence alone isn't going to guarantee an extreme value. And we've actually already talked about an example of this. So if you remember, we were talking about, let's see, I'm going to go to black. There we go. Okay, so for instance, we were talking about the cubic function. Again, we have a place where our derivative is equal to 0, but that's not an extreme value. So we are really trying to find something called critical values. So a critical value is going to be a point where the derivative is equal to 0 or the derivative is undefined. It's a candidate to be an extreme value, but it's not necessarily one. So there's a couple things we need to keep in mind. So here's going to be our test to find our extreme values. First, let's try to figure out where the derivative is equal to 0. Try to find our critical value. We're going to try to figure out where our derivative is undefined. And we're going to take our endpoints into consideration. So any function that we have, we are going to examine potentially 3 different things. And you might be thinking, well, why does the derivative have to be undefined? Why does that give us a place where we might have an extreme value? Example 2, our next example that we're going to look like, is actually going to illustrate this pretty well for us. So let's go down. Oh, and before that, hold on. I completely skipped something important. While this test is going to give us, at least for our critical values, I'm going to abbreviate that CV, while it gives us potential extreme values, our critical values, we are going to need to check to see where a function changes sign. So a function has to change from increasing to decreasing or vice versa to be an extreme value. And really, if we think about any function, we have some critical values. Well, that makes sense. I see that we're increasing here, then we get to a max, and then we're decreasing. Then we get to a min, we were decreasing to increasing. So we're going to try to see where our function is switching from increasing to decreasing, or vice versa, to find that actual critical value. And remember, our endpoint might also be an absolute max or min. We're going to keep that in mind. So example 2, we're going to use analytic methods, so meaning we're not going to use a calculator, and we're going to determine the extreme values of the function f of x equals 2/3 x, and we're going to consider that over the closed interval -2 to 3. All right, so let's just try to picture what this graph looks like. I know that it says use analytic methods, but let's at least try to envision what this graph looks like. So, over here is my function. So this is what our function is looking like, and we're looking at it from -2 over here to +3. So that at least gives us an idea of what we're looking at. Let's actually confirm what our absolute max and what our absolute min are going to be using calculus. So, first thing that we're going to need to do is we need to calculate the derivative so we can test for these values. So over here, if f of x is equal to x to the 2/3 power, that means f prime of x. All right, well, that's going to just be our power rule. We're going to bring down our 2/3 and our last, what am I trying to say? Oh yeah, our exponent, -1/3. So, I might clean this up just so I can see what it looks like. It's going to be 2/3 times the cube root of x. So that's our derivative. So first, let's try to find some of our critical values. So one critical value could come from where the derivative is equal to 0. So okay, let's set it equal to 0. Alright, okay, so if we try to solve for x, let's see, that would include us multiplying both sides by 3 cube roots of x. Well, okay, that's going to leave us then with 2 equals 0. Don't have any variables left, so there's no place where the derivative is equal to 0. Alright, okay, so that was that first one up here. That didn't get us any critical values, so let's try the next one. Let's see if there's any place where our derivative is undefined. Okay, well, if we're looking at our derivative, I know, let's see, let's try that again. 3 cube root of x. Okay, so where is it undefined? Well, that's going to come from where our denominator is going to be equal to 0. So, okay, if I set my denominator equal to 0, that really looks like that's going to be where x is equal to 0. So here we have our first critical value. And I think that's going to be our only critical value, since setting the derivative equal to 0 did not actually give us a critical value. Okay, so we have a critical value. Neat, okay. So what we're going to do is I'm going to throw these into a table so I can see what my potential values might be. So we have one critical value. We also need to keep in mind what our endpoints are. So making a table, here we have it. Okay, so I have -2, I have 0, and I have 3. So those are my 3 potential places. What we're going to do is we are going to use a sign chart. That's something I know that you did in pre-calc. And we are going to test to see where around our critical value we are increasing or decreasing, so using calculus. Let's see if I can get myself a little bit more room. Okay, so if you remember from pre-calc, I don't know if this is what it actually looked like when you did it, but this is how we're going to do it in calc. So we have our endpoints, -2, 3. We have our critical value, 0. And I'm also going to set up a couple other things. We're going to look at where the derivative is positive or negative, and we're going to imagine what that looks like on the graph of f. So this means, okay, now that I have this, let's find some test values to plug in so we can see what the derivative is doing around our critical value. So, I don't know, I always think a good critical value is -1, or test point is -1, and let's see, +1. So if we go to plug that in, so let's see, f prime of -1. Okay, well, let's see. So that would be 2/3 cube root of -1. That looks like it's going to be negative. And really all we care about is that it is a negative. Doesn't matter what the actual value is. Okay, and then if we plug in 1, f prime of 1, so going up to the derivative, that's 2/3 times the cube root of 1. Okay, that's going to give me a positive. So, since the derivative was negative, that means that our slopes of the original function f are negative. So, that means that our function from -2 to 0 is decreasing. And then here, okay, since our derivative was positive, that means that our slopes of the original function are positive. So that means that we are increasing. Okay, so now we know kind of what this looks like. This is giving me at least a vision that our critical point, our critical value 0 is some sort of minimum. But let's check to see if it's a local minimum or an absolute minimum. And so that means we're going to come over here. Let's actually calculate what the function value at these points are. So just so we can see that it is, we can make that determination. So plugging in -2, that's our endpoint. I know that we could grab our calculators and we can do this, so I'm just going to give it to you. That's 1.588. Plugging in 0, that's going to give us an output of 0. And plugging in 3, that's going to give us an output of 2.080. So from here, since I know that my critical value is actually an extreme value, we can make this determination. So I'm going to come over here and let's actually report our findings. So at -2, I see that I am going to have just a local maximum because it's not the highest y value. So I'm going to say that we have a local max of, and then I'm going to actually state what that maximum value is. So anytime we're reporting maximums or minimums, we're talking about the outputs or the y values. So we have a local max of 1.588, and that's occurring at the x value of -2. Okay, let's see. So we have 0. That's our absolute minimum. That's the lowest value that we have. So we have, let's try that again. We have an absolute min of our y value is 0, and that's occurring at x equals 0. And then, okay, at x equals 3, we have our absolute maximum. So we have an absolute max of 2.080, and that's occurring at x equals 3. Eventually, as we move on, we're going to learn how to justify this using calculus. We're going to use the derivative to reference and explain why we know that we have a local max or an absolute max or anything like that. But right now, we haven't learned that theorem yet, so this is all that we are looking for. And we're going to find the extreme values for where they occur for the function y equals x over x squared plus 1. So one thing you might notice is that we aren't given a specific domain, so that means that the extreme value theorem isn't going to apply. So that means that we're not going to have, or we might not have a maximum or a minimum, and it definitely means that we're not going to be able to call them the absolute maximum or minimum. We're just going to call them either local, or we're just going to call them max or min. So with this, we're still going to try to find our critical values or our other potential points. So remember our test. Here, let me get my computer a little more situated. Okay, our test for finding these values, we're going to look to see where the derivative of the function is equal to 0. We're going to look to see where the derivative is undefined. And normally we would look to see, we'd look at the endpoints. But because we weren't given a defined domain, we're not going to look for the endpoints. So, okay, kicking us off, that means first thing we need to do is we need to find the derivative. So let's find y prime, and we're going to use the quotient rule. So it's going to be low d high, so x squared plus 1, low d high times 1 minus high, and then d low, draw a line, square below. Okay. And one question that I get asked a lot, or is asked a lot, is do we need to simplify the derivative? Well, okay, if the question is just saying find the derivative, no, you don't need to simplify. If the question is saying, okay, find the derivative and then do something with it, then yeah, you probably need to simplify. That's what we're doing here, so I am going to simplify this. So let's see, this is going to be x squared plus 1 minus 2x squared over x squared plus 1 squared, and then simplifying our numerator, it's going to be negative x squared plus 1 over x squared plus 1 squared. And I'm not going to expand out the denominator. Let's just leave it like this. So first thing, let's look to see where the derivative is equal to 0. So negative x squared plus 1 over x squared plus 1 squared equals 0. Okay, well, if we were going to do this, solving for x, first thing, we'd probably multiply both sides by the denominator. That's going to lead us to negative x squared plus 1 equals 0. Okay, well, that's going to be 1 equals x squared, and so that means that we'll have x equals plus or minus 1. So I'm going to come over here, I'm going to make a list of our critical values just to keep track of them. Our critical values that we have from the derivative being equal to 0 are we have -1 and we have +1. All right, okay, now we need to examine where the derivative is undefined. So y prime undefined. If we're going to see where the derivative is undefined, that's going to come from where the denominator is equal to 0. So I'm just going to set that equal to 0. So x squared plus 1 squared equals 0. All right, well, taking the square root of both sides, now we'll have x squared plus 1 equals 0. That's going to be x squared equals -1. So that means that we'll have x is equal to square root. That'll be plus or minus I. So, okay, we've delved now into imaginary numbers. Well, okay, our graph is only ever going to be defined over the real numbers, so that means that these aren't going to be important. So okay, so those aren't going to be on the graph. So that means that our only critical values that we need to look at are -1 and +1. Okay, so coming down below, let's see, I'm going to make, come over here to do this. Let's make a chart. We have -1, we have +1. We'll calculate what those actual values are in a moment, but now let's make our sign chart. All right, so this is just an open interval, so really we're going from -infinity to +infinity, so we don't have any endpoints we need to keep in the mix. We're looking at -1 and +1. And remember, we are going to look at a couple things. We're going to look to see if the derivative is positive or negative, and we're going to think about what that means for the graph of f. So, okay, finding some test points. I like -2, 0, and 2. You can use anything, but those are my favorite. All right, so let's see. If we were to plug -2 into our derivative, we're only checking to see if it's positive or negative, so I don't actually need to know what the point is. So let's see. -2 squared, negative, okay, so that's going to be -4 plus 1. Okay, so the numerator is negative, and then it looks like our denominator is just going to be positive, so that means that this part will be negative. So that means that our function is decreasing over this interval. All right, okay, plugging in 0, let's see. 0, that's 0 plus 1, positive. Okay, so over this interval, the derivative is positive, so that means that our function is increasing. And then plugging in 2, all right, so that's going to be negative in the numerator, positive in the denominator, so the whole thing is negative. So again, function is decreasing. So what I can see is at our critical values, -1 and +1, our function is changing sign, or our derivative, excuse me, is changing sign. So that does mean that they are extreme values. I'll write that down, why not? All right, and so let's just go ahead and report our findings down below. We'll do this in black. All right, so we have a local, let's see, minimum. Oh, hold on. What am I doing? We need to actually calculate what our function values are there before we report. Why didn't anyone call me out? Okay, so if I plug -1 into our function f of x, let's see, we'll have -1 over 2, so -1/2. And then 1, let's see, 1 over 2, +1/2. All right, okay. Now that we have those values, we can say what our maximum and minimums are. So we have a local, max of +1/2, and that is occurring at x equals 1. And then we have a local min of -1/2, and that is occurring at x equals -1. So, like I said in the last video, eventually we're going to learn how to justify this using calculus. Right now, let's just state what we have. All right, that's all for this video. I'll see y'all later.